It's my absolute pleasure to introduce Eyal. They'll be presenting lessons in decision making from the Monty Hall problem. I'm looking forward to hearing your talk. Over to you, Eyal.
Hi, good morning, good afternoon, and good evening to everyone listening, wherever you are. My name is Eyal. I'm based in London. Thanks, Chun Chung, for the introduction. Today, we'll talk about something a bit lighthearted, the Monty Hall problem. If you haven't heard about it, prepare to be perplexed. If you have heard about it, and it's quite popular, then hopefully I'll shine a light on aspects that you may not have considered. The nice thing about it is it's something that you can bring up in a social activity, and also you can use it in serious discussions about statistics as well. As such, what I'll show today is that there's many decisions in data decision-making lessons from the Monty Hall problem. So before I start, I want to mention that the slides are always going to be available at this link throughout. You'll see this link if you don't copy it right now. And a more detailed version of what I'm talking about today, I published in an article in Towards Data Science about a year ago. So the premise is the following. Imagine that you're attending a game show and you're presented with 4 doors. Behind one door is a prize, something that you like a car or maybe a vacation, whatever you fancy. And behind 2 of the other doors are something that you don't want, let's say a goat, for example. So 2 goats and 1 car, you have to decide where the prize is. So without lots of generality, let's say that you select the first door, we'll call that door A, and then the host, his name is Monty, he opens one of the doors. He knows what's behind all of the doors, and he chooses, without loss of generality, he chooses door, let's call it C. Now the question that that is asked is, now you're given the option to either stay with your chosen with A or switch to B. And that's the whole premise of the problem. Is it better to switch, stay, or does it even matter? And so actually, before we start, I actually want to start with a poll, and I'll just publish it and give you some time. You'll have time to answer. And oh, and I just want to mention this poll is for new people. So you have 6 options where if you heard of it, I kindly ask you, there wasn't a 7th option, just write in the chat if you heard of Monty Hall before and that you're not participating in the poll, just so I get the numbers. So I'm interested in those who don't know about this. If this is totally new to them, does it matter or not? And how confident are you? So for example, if you think it doesn't matter and you're sure, use the first option. If it doesn't matter and but you're unsure, that's a different option. So again, 6 options. 3 in terms of what you think the answer is, and the second option is how confident you are. So yeah, so I'm starting to see numbers. I'll give you some more time to think about it. Again, switch or stay, and how confident are you? And later on, we'll talk about the why. So that's the premise of the problem. It appears, if you haven't heard of it, it is in popular media. It was first made popular in this game show called Let's Make a Deal. This is Monty Hall himself, the host, but also in more recent TV shows. You can see it once in a while. And it also appears in problem-solving media. For example, we'll talk about Marilyn Vos-Savant. She had this column in the Parade magazine, and it appears in many statistics books. For example, my whole talk is inspired by a few examples in this one over here. This talk is for you if you make data-driven decisions. That's probably all of you, and there's no prior knowledge required. We'll do a bit of statistics, but no equations, I promise. Just a bit about myself. This is like my trajectory in which I've encountered the Monty Hall problem first time when I was doing my PhD. It's one of those fun things in which once you're perplexed by it, you think you understand it, and then you forget and you have to figure out anew how to solve for it. So that's when I was exposed to it. And then when I started learning causality, and it came again in stats books, I started going into it again and really appreciating it, and hence creating this the article and this talk. So what I hope you to take away from this talk is understanding the problem itself, why it's confusing, and the many and different ways of solving it, and there are many lessons in decision making. Time permitting, I'll talk about applicability of Monty Hall in real world settings. So that kind of sets up the agenda. We'll first solve it by intuition, and then we'll use various approaches, and we'll talk about decisions and, again, real-world applications. So I don't see too many answers. I see only 4 people answered. I don't know if that's due to the size of the crowd or not, but that's what I'm seeing right now. So your last chance to answer. I'll give you, let's say, 10 more seconds. Okay, how many people have actually seen it? Okay, so a few. All right, so very low stats, so not worth mentioning at the moment. But before solving the problem, let's solve it. But let's use an intuition, and a great way of doing intuition. I presented the 3-door Monty Hall problem. Now, intuitively, it's useful to do what's called the n-door problem. So imagine a million doors, or we'll illustrate this here. I drew like 80 doors, and let's say the similar premise. You choose one of the doors without less of generality. We'll call that this door over here, and that Monty Hall knows where the prize is, and he exposes all doors except for yours and one more. Okay. Now the question is again, switch or stay, and what's the reason for the best decision? So we won't do another poll here, and let's see. And we haven't answered the question, but hopefully you already used your intuition to solve for this. If not, then we'll understand how to solve for it. So there's 2 main approaches. There's one by, we'll talk about 2 streams of philosophy in statistics and their different approaches. So the frequentist approach, they account for the fact that there's only 2 doors in both cases, both in the 3-door problem and in the n-door problem. There's only 2 doors, and they say switch or stay, it doesn't matter. There's a 50-50 chance of it being behind each. And yeah, so that's one approach. The second approach is by the Bayesians, and they say actually always switch. And what's the reason for switching? Well, they claim, and soon we'll investigate if that's true. They claim, well, what they claim is that the door that you've chosen has 1/n chance. Like in the 3-door problem, you have a third of a chance, but by switching, you get the rest of the n-1/n. What that means literally, what that means with the 3-door problem is you go from 1/3 from A to 2/3 with B, or from 1/, let's say, 100 to 98/100, or rather 99/100. Sorry. That's the Bayesian reasoning. And so what the Bayesians do, first of all, they use prior knowledge. In order to do that, to get that conclusion, they use the fact that they know that there were goats before. That's what the frequentists didn't account for. They didn't count how many goats were here. They disregarded information. Bayesians use that knowledge, and then they update their beliefs. And so what do I mean by update beliefs? Well, in the beginning, they said, well, each one of these are 1/3. And the trick to the whole Monty Hall understanding why the Bayesian approach is correct is saying, well, each of them are 1/3. That's what we said. But now we have to separate between the original choice to all the rest. And so all the rest get the complementary of 1/3. So that's 2/3. And so the interesting thing is that once you expose one of the doors, well, that goes from 1/3 to 0. And so this 1/3 does not get split evenly between these 2 doors. That's what the frequentists do. Actually, it goes over here, right? Because this 2/3 now is broken down to 2/3 and 0. And that's the Bayesian approach. And that's the correct way to solve for this. And so just to summarize the differences in the approaches, the Bayesians, they account for all the information that's given by the host, and they update their beliefs accordingly. The frequently do not. They just focus on the 2 doors. So here I'm showing the same exact thing. With the, let's say, 100-door case, you have 1/100. This remains 1/100 once you expose, and then all this 99/100 goes into this door as well. So I was curious to understand why, and it isn't obvious for everyone why the, let's say, 100-door problem is more intuitive. With experience, you realize, oh yeah, that makes so much sense. But I try to understand, like, why is that? And I found. So for example, when I look at this, I immediately say, well, the chances of me detecting this, getting this right is very low, that means it's most likely over here. And so that's very intuitive over here. But over here, it's not that intuitive. And so I really have to think about the n equals to 3 and do that breakdown that I've shown before. And so I was wondering, like, how can we quantify, like, why was this so obvious to me and this not so obvious? And so I found a solution in information theory, in which it all has to do with how much information the host is conveying by opening up all those doors with the goats. And that's something that we could quantify. And so I'll spend a few minutes explaining that. I'll introduce only one equation, and that is something called the surprisal. So the surprisal expresses how surprising an event is. In the case of Monty Hall, how surprised we'd be if the prize is behind our door, right? Over here, we said, here we'd be very surprised, but here we wouldn't be that surprised, right? We'd expect it, but over here we wouldn't expect it because there's so many doors. And and this is how we quantify using this logarithm here, and this is called the surprise. So let's visualize what we've done before. So let's say you have 3 doors, and this expresses in units of bits of how surprised we'd be if we open a door. So here we go from about 1.5 bit, and this is logarithmic scale, in which, let's say you have the case of, here I limit to, let's say 60, you'd be much more surprised. And so that's if you, again, the door that you chosen, let's say you stayed. Now, if you switch, that's what the Bayesians argue, then you see that you're very not surprised. The fact that, remember this door over here? Well, you're not surprised that it's going to be there. And so you see it asymptotes to 0 once you get to 60. So there's some element of surprise over here, right? You still might be wrong. But over here, you're most likely you're going to be correct. And so, yeah, so this gap actually quantifies the amount of information conveyed by the host. So you can see the gap is quite small here, and the gap gets larger and larger with the number of doors. And that, for me, that's an answer of why was I not surprised? Why was it intuitive with so many doors and not intuitive without? And so that was one lesson. There's a whole list of other lessons that I came up with, and I like to go through of what we can learn from the Monty Hall. And so the first lesson has to do with the fact that assessing probabilities can be very counterintuitive. And so I like this phrasing by Daniel Kahneman in his book Thinking Fast and Slow, in which he talks about two types of thought processes. On the one hand, you have the fast thinking, what he calls system 1, in which it's based on intuition, meaning you have confidence because you've seen something before. And that's kind of like the frequentist approach in Monty Hall, because they saw 2 doors and their fast thinking said, oh, that's a coin toss, so it's a 50-50 split. It doesn't matter if we stay or switch. But the correct approach is realizing that it is counterintuitive. You have to slow things down. And so Daniel talks about system 2, in which you want to put deep thought into the problem in order to solve something that's complex. And so that's what we've done with the Bayesian thinking, in which we broke it down into the contribution of each door. And so, yeah, so again, when it comes to in the end door problem, it was intuitive. Again, I could use my quick reasoning because we were given so much information by the host, as we quantified before with information theory. But again, when you're given only 3 doors, then you really want to slow things down and do this breakdown as we've done before. So that's the first lesson. The next lesson is search for clarity in ambiguity. So one thing that you'll notice in the way when you go over textbooks and you see how Monty Hall is phrased, and I purposely did the same, is it says the host who knows what's behind the doors, but no one ever tells you that the host opens a door that does not have the car. You have to infer that. And so what I mean by that is when you write down the equations, you have to consider that. So there is purpose ambiguity there, and you have to interpret like what the scene is. Of course, he's not going to point to the car. His whole objective is for you to figure it out for yourself. So he's not going to infer that. So that's what I mean by when you analyze data, you're not always told by the provider of the data what's behind it, and so you have to ask for clarity. The next one, the next lesson that's from the Bayesian mindset is once you're given new information, you should update your beliefs. That's what we've done over here. Here we said 1/3, 2/3. This remains 2/3. Once you open this, 0. So you update your belief over here to being 2/3, and that way you know that you should be switching. I won't get too much into the debate between frequentists and Bayesians, but just one note is that frequentists talk about the fact that Bayesians are subjective because they use priors. The response of the Bayesians is the Bayesians also use priors, but they're not aware of it. They use flat priors, which is a type of prior. The takeaway from this is when we make decisions analyzing data, we're constantly making subjective decisions. For example, when you're looking at distributions, should I report the mean or median? Well, there's interpretation between each, so you have to justify for yourself and then to your stakeholders what's more important. For example, maybe there's two modes and you have to resort to something else. So you have to understand the data, understand the domain, and make subjective decisions accordingly. So this might be a bit controversial. So simulations are very powerful tools to solve for complex problems. And my controversial statement is that simulations are not always necessary. The reason is I say that is in cases like Monty Hall, which is highly analytical, meaning you can write down pen to paper a solution, you do not need to simulate. And I raise that because in some problems you see people trying to use simulations for Monty Hall. For example, this popular TV show called Mythbusters, they literally have whistles and bells in which they simulate many scenarios of Monty Hall, just running simulation after simulation, just to get the conclusion that you should definitely switch. But as I've shown before, this problem is analytical. You can solve it. You don't need complex simulations for that, whereas you would need them in complex problems. So I'll be a bit cheeky here. Sorry, another lesson is a well-designed visual really goes a long way. And so Marilyn, she proposed many solutions to this problem, as we'll see later, because there's a lot of people actually didn't trust her original believing. If you said that the doors, that it doesn't matter if you switch or stay, well, you're actually in good, even though you're wrong, you're in good company, because many people, leading mathematicians actually thought that was a 50-50 split, and there was a controversy at the time, and Marilyn, like, she was like publishing a lot about why the Bayesian is correct, and she was getting a lot of backlash. And so one of the things that she's done over here is she posted actually a nice visual. I won't get into it right now into detail. Again, you'll have to put on your slow think system 2 hat on in order to understand it. But basically the premise is that she boils it down to, well, this problem actually has only 6 types of gains listed here: 3 of switch, 3 of stay. And in the switch, she shows that 2 of them, you actually win the prize, and in the stay, only 1, hence the 2/3 and 1/3. So again, if you want, take a look at this, try to understand for yourself, but it's a very good visual, and it really like explains it. There are other ways like decision trees, for example, which also are a way of visualizing, but I really like this visual because it really brings things home. Again, not for your system 1, but for your system 2. And this brings me to my next lesson from Richard Feynman is considered a superstar amongst the physics community, in which he made the argument that any problem can be solved many ways, and that's what Marilyn shows. That there are many ways for solving this, and that's one thing that we consider when we're analyzing data. The next thing is embrace ignorance and be humble. And the reason I bring that is, again, that many people didn't. Even though Marilyn was considered one of the smartest people on Earth, and she published the right result, a lot of people did not agree with her. And by people, I mean PhDs from universities, at least in the United States. I don't know about worldwide. So yeah, she got a lot of backlash, unnecessarily cruel. But there, yeah, and all these comments are online. But there were like some glimmers of hope of people that actually had positive feedback for her about her solutions. And this brings me to the last lesson, which is when you're confused in solving a problem, look for a useful analogy. So when something appears confusing or overwhelming, try to break it down to things that you're more familiar with. For example, the n=3 solution is kind of confusing, but if you go to like n=1,000,000 or n=100, once you visualize like that, it becomes really simplified, and then you can kind of use intuition and then break it down to when it was harder. And so the whole idea behind this lesson is, if you're stuck with something, try to zoom out and try to get the full picture of what you're trying to analyze. That, of course, comes with a word of caution between the trade-off between simplicity and oversimplicity. There are two useful quotes. One is Occam's razor, which basically says that the most simple solution is most likely to be the correct one. Just paraphrasing this, as opposed to this one by Mencken, in which says if a solution is too simple, it is probably wrong. So it might be useful to use the third quote, which is all models are wrong, but some are useful. And so with that, I think I have some time remaining. I once in a far while see an article in which they talk about an application of Monty Hall in real world setting. And when I read them, mostly I'm not that convinced that it is, that Monty Hall is a good analogy. Sometimes they just mean, oh, we should use a Bayes setting, and that's the underlying message. So I was trying to understand, are there actually real world applications of the Monty Hall setup? And so in the following, I'm going to divide this into qualitative analogies and quantitative analogies. So what do I mean by qualitative analogies? That means that the relationships between the parameters are qualitatively, they're similar to Monty Hall. So what's the relationship in Monty Hall? Well, what are the parameters? The parameters are, you have two independent parameters. One is the door you chose and the prize door. So those are different parameters. They're independent from each other. They don't impact each other. But the parameter that the host chooses, well, it depends both on what you chose and where the prize door is, because he knows where the prize door is. So this is kind of like a setup. And so I had a few hearts with ChatGPT to see, well, what it thinks that would be a real world application. And it gave me a lot of ideas, and none of them were satisfactory. And here I'll give you one which might seem satisfactory, but then I'll explain why I don't think it is. So for example, when hiring and pre-screen candidates. So imagine that you're a manager and you need to fill in a role, and so you have a job description. You've written a job description, and that's independent from all the candidates that are there in the world. And then the HR provided both of them, both the description and the candidates that are in the world, and they create a short list. And so that's a claim for this being an analogy. So why does it break down? Well, first of all, HR don't know who is the best candidate, right? Monty Hall knows where the prize is, and the short list may or may not have the best candidate. The prize might not be there. They might not be available. And another argument is, and here I'll give you C, is that, well, the candidates that apply, well, it depends on the description. Maybe the description is wrong itself, and you get someone who doesn't interact socially. Let's say the social aspect between people isn't in the description, and you get somebody who's very antisocial. And so that means, and the candidates that apply are decide based on the decision. So the candidates are a function of description. And so even qualitatively, it doesn't hold. And so that's why you want both qualitative, but you also want quantitative. And so what's a quantitative relationship? Well, then we have to quantify, well, how is this the function of these? I won't spend too much time on this detail, but this is the actual equation of Monty Hall. So how do you read this? Well, you have these three parameters, X, Y, and Z. Well, they all have, let's say in the three-door problem, they all have three values. You have A, B, and C, meaning door A, door B, or door C. So you could choose A, B, or C. The prize could be behind A, B, and C, and the host can choose A, B, and C. So their choice depends on if you chose the correct one or not. That's what you're reading over here. So here he has two options, and here he's limited. Actually, if you chose a goat unknowingly, then he's left only with what? No, choose. Yeah, if he chose the goat, then he has only one option to choose from. Yeah, because he has only one option to choose from. That's what this is saying over here. So this is the actual equation of Monty Hall. So if you want to be very strict in your analogy, like where Monty Hall applies, then you have to abide to that. So where do you find that? Well, ChatGPT actually came up with this, and this is true. The 3-cup magic trick, right? You have 3 cups. As long as they didn't show you the ball, right? If the ball has been unexposed the whole time, and you have no way of gauging where the ball is, and you point at one and he lifts up another one, this is exactly a Monty Hall problem. So it's a perfect analogy, but it's very superficial, obviously. So where can it be useful? Well, another one that it came up with is adaptive tutoring or penetration test simulation. Well, this kind of has merit to it. So let's say a student is required to ask her a very hard question where it has a true answer, and the tutor gives them hints based on his answer to guide them in the direction. And so this is actually, I think, a good analogy for Monty Hall, as long as it's a hard answer in which the student has no way for answering it. If it's a simple answer, then the student's answer will depend on their knowledge of the domain, and so then you'll have a different structure. So I guess my point is that, again, going back to lesson 9, is use for analogy, but tread with caution. As I've demonstrated, I've been pretty harsh in my definition is what's useful and not as an analogy. And you can either be happy just with the quantitative or actually go into the qualitative with the actual equations. So just before I summarize, I just want to, again, mention that I go further into detail about Monty Hall. Again, a fascinating topic, in my opinion, in this article. So feel free to check it out. I go more into the controversial relationship between Marilyn and mathematicians worldwide in there. I mentioned from information theory. As a data scientist, I use entropy, scale diverged and mutual information, in the engines of machine learning, but I've been really unsatisfied that I actually didn't understand them. And so I dedicated to the first part of this year learning and writing up about my learnings. I created like a five article series detailed over here, in which this first article summarizes the first 3. So if you're interested in understanding information theory, then I recommend checking this out. And finally, one thing I realized in 2020 was I've been doing 15 years of analysis, but didn't realize that causality is important. And so I've been presenting on PyData stages, both global and locally, about causality. And I also started publishing online. So this article is the introduction I needed to causality, about the importance of confounding, and as important when you shouldn't control for parameters that are not confounders. So I talk about that over here. The next one is the importance of something called Simpson's paradox, which is a potential misinterpretation of data to understand it and solve for it. And so I warn you, once you read this, you'll never look at data the same way once you understand Simpson's paradox, which is a good thing. And finally, final article is, even though if you know causality, you can't always apply it in real world settings. So that's one question. But what I realized with causality, even if you can apply it to real world settings, just assessing if it's the validity is useful for mental hygiene and data science projects. And so that's I write about this over here, and really like putting a causal framing on problems in data, as I've demonstrated here in the Monty Hall. I find this very useful. So with that, I'll just end with the lessons. My contact is over here, and the links to the materials over here. And with that, I'll be glad to take questions.
Right. Excellent. Well, thanks for the super nice talk here. I think it was super very, very informative. I'm going to switch the view over here, and then we'll take a look and see if there's any questions from the attendees. Feel free once again to use the Q&A icon, where you can type questions, and then we can filter them as well. So far there isn't any, but maybe I can just kickstart by just asking one super general question.
Sure.
I know about causality in my past work as well. So in your experience, when you speak to any stakeholders, was there a more preferred way of explaining causality to the people that you work with?
It really depends on one's settings and how comfortable they are in the details. It really depends where they are. I mean, at first, causality is first of all, it depends on the domain, like how possible it is to do causality, because a lot of real world settings, it's actually not possible. And so most of the time it's about like, first of all, finding correlations within data, and then trying to identify possible confounders. And and address those. One more thing that I've realized is when you have selection bias. When you have selection bias, that's a case in which you can do an analysis to learn about your data, but you can't infer causality from that when you have a strong selection bias in certain settings. And so that's another lesson that I've learned in that. So possibly not a satisfactory answer. Just in general, I recommend, regardless, causality is very intellectually stimulating. So there's a lot of advancement in the past 10, 15 years or so, and it's really like mind-boggling. And even if, again, you can apply it to real-world setting, you learn a lot about your data just by thinking, putting the causality hat, solving for potential paradoxes in your data. I had a paradox in machine learning interpretation, and I resolved it by applying causality. So I was really proud about that. And that's part of my article in which I talk about my experience with that. Yeah.
Excellent. Thanks for sharing that. I'm just taking a look at the Q&A once more. Nothing seems to be trickling at the moment. But I suppose that's all the time that we have for today. Thanks everyone for attending the talk. It was super nice to hear this really, I guess, whistle stop run through from Eyal. Feel free to continue discussions. You can head over to Discord, take discussions over there. Eyal has left his contact over there as well, so feel free to just ping them and stimulate more conversations. With that, thank you very much. I'll end the session over here, and I'll see you in the next couple of events. Thanks, everyone. Bye-bye.
All right.